Great. Can you guys hear me? Okay. Okay, great. Yeah, thanks for coming, guys. So I know I'm the last session for today, so I'm kind of been awake, but hopefully this is useful and entertaining for you guys. Part of the talk title is Universal Code Execution for by training messages in browser extension. And this was kind of inspired of two things. Firstly, I think the conference organizers really wanted some web talks, and it's kind of hard to think of a good web talk, in a zero-day kind of bound research conference. So I was trying to do something different. And the second thing is that I really like client-side attacks. I think it's interesting, gives you an opportunity to test, do more white box and gray box stuff. And that's kind of the reason for today's research. So I'm Eugene. So I kind of blog at this spaceraccoon.net. I am a security engineering lead in a day, so I do good stuff for the government, and we are hiring. So just my little shill for today. And hacking is my hobby, so I do like researching after hours at night, and this is kind of one of the little projects I worked on back then. And so for today's talk, just going to go through a quick outline. Going to give you some background and prior work on extensions research. Especially, I think one of the more updated parts is Manifest v3 and the Web Extensions API internals. And I'm going to talk about the first part of the chain, which is from post message to send message. So for those of you who are more familiar with web-based attacks, you know that post message is a client-side attack, and how do I kind of bridge that gap from a web page out of the sandbox into the extension context. And the second part, I'm going to talk about a quick finding that in extension A just to illustrate how this can be exploited. And then I'll go to the next part, which is a bit more interesting. How do you then cross the bridge from the browser extension context to the desktop native context, right? That's from send message to send native message. And how that has changed with Manifest v3 from current prior research. And then I'll talk about extension hunting at scale, right? So I think the part is how do you then scale this research across millions or hundreds of thousands of browser extensions all at once. And that's kind of one of the things that I think is more exciting about this research. And I'll talk about code execution and extension B. So you know that these are not real names. Unfortunately, I disclosed them in April, but none of them have patched it yet. But I thought it'd still be interesting to go through and show you a video of the expert. And I'll go through a conclusion and further research. Cool. So let's start with some background. I think some of you may have heard about universal cross-site scripting, right? And they call it kind of like the most powerful XSS. And why is that? Because it's not a vulnerability in the web page, not in the HTML, not in the scripts. It's a vulnerability in the browser itself, or in some cases, extensions, because people kind of use extension vulnerabilities to trigger that. And what this means is that the XSS triggers on any page, regardless of what kind of scripts are in the DOM of the target website. So as long as you visit somewhere with a malicious website, or maybe it's part of the URI, recently I think there's some really cool research in the macOS Safari Universal XSS, you can check that out. And then the JS is executed in the context of any website. So it's no longer limited to one website, but any website. And that makes it kind of almost like a safe origin policy bypass. Can we take it one step further, right? And while I was actually like halfway through my research, I had an unfortunate experience where you kind of search what you've been doing and you realize someone has done it a little bit before you, right? And as early as 2017, researchers have looked into extensions, right, and have found a lot of weaknesses. So I think this is something that's presented at OWASP by Arsen in 2017, looking into post-message security in Chrome extensions. How do you bridge the gap from a web page to the browser extension context? And then we'll see how much has changed since then, 2017. The spoiler alert is not much, right? It's still exploitable, it's worse. Somehow that seems to be a common pattern these days. So let's start with some background, right? Browser extensions comprise of a few key components. The first is the manifest. They tell you exactly what's in the extension. It tells the browser how to interpret the rest of the extension parts. The second is the content script. This is scripts that are injected into the web page by an extension. So how the extension can interact with your DOM, if any web page that you kind of give the permissions to. And the second part is the background script or the service worker. Background scripts were used in Manifest v2. The more recent Manifest v3 uses service workers. The main difference is that service workers are short-lived, but you can still make them kind of last a bit longer. And finally, we can talk about the native messaging host. So some of you may use password extensions, maybe you use like 1Password, and you've always maybe wondered how the extension can talk with your 1Password app that you've installed on your desktop. This is how it does that, right? And we'll kind of investigate that a bit. So let's do some code review. So firstly, the manifest declares a few things. It declares the service workers, the content scripts, and more importantly, the content security policy and permissions, right? And there are a ton of footguns available where developers can make mistakes or have overly permissive permissions. One of the key things is, let's see if we can highlight that. One of the key things in Manifest v3 is that you no longer have a background script, you have what they call a service worker. This is what you define as the script that runs in the kind of browser extension context. The second thing is the content script. The content script is what's injected into a web page by the extension, because sometimes the extension may need to interact with your document object model, your DOM, right? What's on the web page, may need to insert something, read something. And one of the fun things is that you're not supposed to actually inject the content script into every single page, right? You're supposed to kind of specify what URL that you would then inject the content script into. But what I've seen is that a lot of developers just don't care, and they kind of set it as either all URLs, or they kind of have wildcard matches and kind of appears in every single page. But the great thing about all of this is that it makes it really easy for you to identify potentially vulnerable extensions, because you can kind of have this starting point where you see manifests and you parse all the manifests to figure out if it may be something that you may want to dig into a little bit. So the second part is content scripts. So I mentioned that you can inject scripts into any page, right, by your extension. Now, of course, that does sound a bit scary, and that's why, actually, by extensions, they are injected into what they call isolated roles. So that is Chrome's terminology for that. Basically, even though you inject it into a page, it can access the DOM, the document object model, but it cannot access other JavaScript variables by the scripts that's running on the page, or even other content scripts. A second thing with Manifest v3, Manifest v3 is basically kind of the latest generation of extension specifications, is that there's very strict default content side policy, right? So it prevents most of the inline JavaScript execution in XSS. This was a big problem, maybe about like 5-6 years ago, where the extension would read something on the DOM, on the document object model, and then it would kind of eval it, and that would lead to an XSS at the extension browser context. But this has kind of been eliminated a lot by a strict default CSP. And also there's a limited browser extension API available to the content scripts, not the full browser extension API, but just enough for them to talk with the background script. So I'll talk about that. So as I mentioned, the content script that's injected in your page can't do a lot, right? It can read the DOM, it can insert, change stuff. I don't think they even make a fetch call unless you give it sufficient permissions. So most of the time, for more complex functionality, what they do is that they pass messages to the service worker that's running in the browser extension context, right? So the content script will execute chrome.runtime.sendMessage. There are multiple APIs that allow them to communicate back. And what the background script will do is then take that message, do something with it, and if necessary, call back to it by just sending a message back, right, to the port or the socket. In this case, you can just look for add listener on message, very simple, not very complex way of content message passing. There is also cross-extension messaging. It's possible in some extensions, but it's fairly rare. So most of the time what you'll see is a background script talking, send message back to the content script and vice versa. But you can see that the context is all kind of separate. So it allows them to kind of stay safe in isolated roles. So let's talk about the first part of the chain today, which is the post message to send message, right? And to communicate from a page.js to the extension, post message is used in the shared DOM, right? So what do I mean by that? So say, for example, you have a web page, right, that is supposed to interact with your extension that you've installed. Maybe you've installed like, I don't know, like 1Password extension, right? And you're visiting the 1Password homepage. And maybe they kind of want to like talk with your extension when you're visiting the 1Password homepage. How does it do that, right? Because as mentioned, in the DOM itself, there are isolated roles for the in the JavaScript context. So they can't actually talk to each other. But they can both access the DOM. And one of the great things that you can do then is then send a post message to yourself. So the website will make a post message call to itself, and this post message is actually it's able to be picked up by both and all content scripts on that page as well. And so this is actually a pattern that's recommended by the Chrome documentation, where it's like, hey, if you have a web page that you want to talk to your extension, use the post message pattern to talk to it. So what you do is that you send a post message to itself, and the listener in the isolated world, say content script A, will pick up that post message to itself. Sometimes you do some validation, like making sure that it's really from the same page, and that's how you get that a message from the DOM. However, one of the things is that post message was never really meant to be used like this, right? I mean, you probably know that post message is a pure browser-side, client-side API. It's just for frames to talk to one another, sometimes cross-origin. It's never been meant to be used in the extension context. It's kind of been janky, but that's how we are able to have that separation in isolated worlds, but still share the same DOM, right? And this means that typical ways of validating the origin of a post message are now nullified with weak manifest matches. So in this case, for example, what you typically see in pure client-side code with no extensions is that they will validate the event source and make sure that it comes from the same window, right? So it's like, oh, hey, it's either my parent or a child window or my own frame that's talking to myself. It's not coming from another origin that is trying to talk to me. In the case where you're using this in a pattern of page post message talking to the extension content script, this is actually useless, right? Because it doesn't actually matter. It's always going to be the same. So now you can kind of bypass that, and this makes it even more dangerous. And as I mentioned earlier, this is effectively nullified when you have weak extension matches, manifest matches, where the content script can be is injected in every single page, regardless of the URL. So very quickly, we can talk about a case study with extension A. And in this case, it has very weak matches. You can see it here. It has a few permissions. It has the cookies permission, and you can access the cookies of website A, website B, and all the subdomains of website C. So obviously, I think it was meant to just operate on all these websites, but the matches doesn't kind of line up with what permissions is been granted. So in this case, how this works is that we would have a add event listener on the web page, right, in the content script, and on receiving a post message, it would actually forward it to the background script using the chrome.runtime.send message. That's how it talks to the background context. And in the background script, which is running in the browser extension context, it will kind of get the listener. You will check whether the action is a specific action it's listening for. In this case, get cookie. You would execute get cookie, retrieve it, and then send it back using chrome.tabs.send message, right? And this is really like super simple, straightforward exploit. You'll see this a lot happen in more weaker extensions. So this is something that you can exploit very easily. Just runs on any domain. So as long as they have this extension installed, as long as they're visiting your payload regardless of domain, you can then eat the cookies of website A, website B, website C, and this breaks same origin policy. So this is one of the extensions installed by more than 300,000 users and very simple POC. We're still kind of on very well-known ground here. Most people looking at extensions would see this. So let's talk about something more interesting. How do we extend this exploit from just the same origin bypass, policy bypass, to something more interesting where you have a browser sandbox, a breakout, right? Not exactly a breakout, but it's kind of an at-level breakout. And that's by going from send message to send native message. So how does your 1Password extension, and again, 1Password is not the application that I'm talking about. Don't worry, keep it. How does your 1Password extension talk to your desktop application, right, that's installed in your desktop? How this is done is that there is a part of both the manifest v2 and the manifest v3 browser extension APIs called native messaging, where native applications can register native messaging ports, which is just a binary executable running, using a manifest file as well, right? And so for Chrome, you can register it at this registry key, and you just tell them, this is the location for this application of my manifest. And in the manifest itself, you kind of specify a few things. Of course, you specify the host name, which is, in this case, just my application. And then the path. where the Chrome will help to forward those messages to, in this case, Chrome native messaging host.exe. And there are a few other additions where you can add loud origins, right? In this case, Chrome extension, which Chrome extension can actually trigger this standard input. They have a type of the input, but actually there's just standard I/O, which I'll talk about a bit later. But this is basically how it's going to communicate. It's going to be standard in, standard out, very simple, typically just string JSON encoded. So in this case, background scripts can then, or extension service workers, in the case of manifest v3, communicate with this native application host via the browser. Right? So this is very similar APIs, but for native messaging. The second thing is just, as I mentioned, it just uses standard in and standard out. So it's very simple parsing. You don't really see very complex encoding. Most of the time it's either base64 or just JSON. It's just plain text. And if this message is handled dangerously, then the native application can be exploited, right? So in this case, we'll see a very simple pattern, again from the Chrome documentation. This is running in your background script or your service worker, so in the browser extension context, not the content script. It will send a message to the host with your text, and it will also be able to listen from it to receive the output from your native host application. And this is something that you can then string together to get what we, it's just a term, universal code execution, right? Think of it as similar to universal XSS, but in this case, you're making one more jump from the browser extension context now to the desktop host application context, which means code execution, right, outside the browser. We start with step one, where your browser extension has a wildcard pattern for content script, so it's kind of weak, not super necessary, right? You can run on certain websites. You can find a vulnerability on your web page as well. Put one more link in your chain earlier on. Second is that the evil web page or the injected script then sends a post message to itself in the same frame, right? And in this case, the content script will be listening. It will be able to pull that post message, and then it will pass that message on to the background script using send message. The background script gets that message, then does some stuff with it, and then finally forwards it to your native host application using send native message. And then, of course, the native application handles the message dangerously, leading to code execution. So you might think, okay, that's cool, right? Probably only happens to one or two applications, extensions. There's a lot of parts of this chain that need to do that to work. So let's talk about extension hunting at scale, right? I'm not going to go and look at every single extension out there one by one and try to figure this out. So we can do this at scale, and this is kind of one of the fun parts of vulnerability research these days. If you have an idea, you can scale it using whatever pipeline you have. So there are a lot of actually existing databases that make it easy to query browser extension manifest at scale. One of these is Chrome extension manifest database on GitHub, right? It has a dataset of about more than 100,000 extensions, and basically this guy scraped all of the manifests for all of the extensions he could get his hands on for you to make a query. He also has quite useful scripts for you to then parse all of this data at scale, because you can use grep, right, or JQ, but it's going to be kind of not necessary if you just use the script. And then you can add a few filters for that. So in this case, what I started with was that, okay, I want to find maps and extensions that may be used by a lot of people. And I'm going to filter whether they have a content script and whether they include a permission that includes native messaging. Right? So there are two parts of the chain that are available for me, and there's some likelihood that this can be exploited. So after filtering for promising manifests, I would then download and extract the extension and then scan them with a custom sandbox rule. Because remember, there are two other parts in this chain that you want to connect. The first part is the post message handler, and then the second part is the send native message function. And this is something you can do with tools available these days very easily at scale. My favorite here in this case was Sandbox. You can use the taint source and taint sync, and then just do a standard taint analysis at scale across maybe how many manifests that you've filtered down. In this case, I look for a few things. I look for either Chrome runtime.sendMessage, or I search for port.postMessage, because there are multiple ways that you can express sending a native message in the extension. For pattern sources, I also had to kind of add a few more filters. In this case, if you're kind of a sandgraph, you've used sandgraph before, you recognize focus meta variable, pattern not. These are ways to just make sure that I don't get false positives. And so I think just with large enough funnels, you'll always get results. So I started with more than 100,000 extensions, and then I did the query to filter potential manifests, in this case about 200 plus. And then by running my sandgraph rule, I can then narrow it down further into 31 kind of service workers background scripts that seem to be vulnerable. And followed by that, I kind of have to make sure the last part of the chain is available, which is manual review of the native host application binaries for exploitability. In this case, you start seeing a few interesting patterns with the types of applications that would use this kind of pattern. In this case, I found something with PKI card extensions, and I'll talk about why that is. So let's start with the case study here with extension B, right? So extension B is used by more than 2 million users, and this is an extension that kind of fills a common gap in browser extensions in that it adds PKI smart card support in browsers. As you may know, the browsers, a lot of them don't support PKI smart cards by default, right? They support the web plan standard, so that's FIDO, passkeys, but they don't support PKI smart cards. The problem is that there are a lot of enterprises out there that still use PKI smart cards, and this is why extensions are very popular. In this case, they had more than 2 million users, but I'll tell you that this is not the only extension that had this pattern, that had this number of users, because everyone kind of wants to fill the gap. And by design, in order to enable PKI card support on whatever web page you use, by design, you're going to have a wildcard extension matcher. In this case, as you see, we just use the star for the scheme, the URI, and the path as well. And fairly standard, you can see that they have permissions for native messaging. So let's try to link this up all together, right? We'll start with the content script. And what the content script does is, again, that it checks, they try to be secure. They check whether the event source matches the existing window, which, as I mentioned earlier in this presentation, is useless, right? As once you have a wildcard matcher, the event source can be any page that you control. And so you can send a message to yourself, that's always going to pass the origin check. The second thing is that it forwards the event data to the background with the sendMessage API. The background script as well, again, it does a few checks. It checks for the action type, but it doesn't really do much more than that. So it immediately forwards that to the open native messaging port via chrome.runtime.connect-native that is open previously. And of course, your native host application passes the standard in as input as JSON. And then it just, well, you can tell this is just one of the actions that it runs to load a DLL at the provided value that is given in the message. So since native messages are standard input, it is really, really easy to identify the entry point. And this is, again, this is kind of part of the code that was the handler for this. What it does is that it just takes the argument from your native message, appends it to C Windows System 32, and then loads the DLL at this path. And this is a very common traversal pattern for DLL loading, not complex at all. Just like the shield that I think Winston, you're here. Yeah, Winston and I, my former colleagues, we worked on a Zscaler client connector solution that also had DLL loading that it's interesting, so go with that. But other than requiring a known download path, it's not overly complex, very simple, and something that I think for most attackers you should be able to get around. So in this case, what do you need to do? You first need to trigger the download of the malicious DLL, and then send a post message payload that would then trigger the native host application to load and execute the malicious DLL. Standard, you can use the DLL hijacking, but in this case, it's not a DLL hijacking. So it's a simple two-stage POC, as I mentioned. The known download path is an annoyance, but often native host applications have very inexplicably weird features like get info or get username. You see some weird things in this space. One of the side notes is that actually there are some browser extension APIs that actually allow you to specify your download path and trigger a download anywhere on your computer. right? So keep an eye out for that. In this case, the POC does firstly triggers the download payload. It just creates a form and then a link and clicks it. This is a bypass that most people use because in order to trigger a download, you have to, browsers make sure that you have to click something or have some kind of user interaction. So this is one way to quickly simulate that using JavaScript without any user interaction actually. The second thing is then you send a post message. In this case, you have to add some standard values that will help you get around the various checks of both the content script as well as the background script, as well as the native host script, host code. And in this case, we're going to select the action, and we're going to specify that the library is going to be kind of in your download folder and the payload that you specify. Okay, so this is kind of what it looks like. So again, I didn't the extension, but I don't know the function names. Okay, so it triggers the download for the payload.txt, and it's going to pop the calculator. So this can be run on any page as long as you have this extension installed. You were hoping to use a smart card, but I think you're going to get a different surprise that day. But this means that you're vulnerable regardless of where you visit, right? And you can inject it anywhere. Very simple to exploit. There are even some, because they inject the content script, it's also fairly easy to ID if someone is using this vulnerable extension that you want to exploit. Cool. So, okay, time's running out. So I'm going to talk about the conclusion and some of the learning points from this. Right? As I mentioned, this is something that was maybe raised a few years ago, and Manifest v3 for Chrome extensions, browser extensions, MDM also, MDM defines this as Manifest v3. Were meant to improve the security of browser extensions. But this was mostly in the client side where they added content scripts and also limited kind of the permissions you need to request before you can execute the browser APIs. But it seems that vulnerable browser extensions are a feature, not a bug, right? I know there's been a lot of work in browser extensions, especially in the crypto space, primarily because you have MetaMask and other similar extensions. But it's really, really hard to secure Chrome extensions. And for researchers, it's great because they are white box research by default. So you have access to all the code and you can analyze it from there. There are built-in foot guns at every level, right? So for example, as I mentioned with the PKI card extension, just because by definition, the PKI card extension needs to run on any website, they're going to have a wildcard extension mentioned. Okay, fine. And there's a full understanding of risk posed by extension permissions and messaging chain. So as mentioned, I did actually a fairly strict funnel where I filtered 100,000 applications. But this was because I was pressed for time and the CFP was coming up and I needed to get a result quick. But if you actually extend this a little bit bigger, in terms of what kind of sources and sinks that you're willing to tolerate, as well as whether you're willing to spend some time to maybe find a bug on the website instead of a wildcard origin, you can actually find a lot of interesting things. So there's full understanding of risk by developers of having this kind of through train, kind of a pass-through, right, from the content script to the background script, and finally to the native host application. And what I've seen most of the time is that there's a lot of trust at the native host application level of the messages they're getting from the Chrome extension, primarily because for native host applications, the manifest allows them to kind of restrict messages from a specific Chrome extension, and most of the time, like, it's going to be there. Another interesting thing here is that just by understanding that there is this vulnerability in your native host application, you are now also very aware of the fact that even if it's not coming from a Chrome extension, this application is vulnerable, right? And it just needs to take it from standard in. And this leads to very interesting questions of, hey, is this extension running in a very privileged context? Is it a password manager? Is it running as a privileged user, right? And this does happen, especially for these kind of extensions that need that interactivity between the browser and the desktop. And it's still very under-researched. So I mentioned, as early as 2017, people have been kind of thinking about this. But there's a lot more research that needs to be done in Manifest v3 APIs. Manifest v3 brings about a new set of APIs, new set of permissions, restrictions, But it also lets a lot more experimental features, such as maybe the Credential Manager API. There's also some side work I've been doing on WebAssembly VM APIs, but that's still in exploration. So yeah, that's it for the chain. Jill, again, I'm hiring, talk to me. But if you want to find out more, I'll put up a blog post that kind of summarizes the learnings from today and on my blog. So thank you very much.
Thank you, Eugene. For the last session of day one, we open the floor for any questions. First question from Trevor.
Okay, so have you monitored any or observed any similar type of issues in communications in the WebSocket area? Because there are also some extensions we could have done asynchronous communication instead, right? And it's totally different, but the delivery is still the same. So have you observed any of that?
Yeah, I think that's interesting. So I mean, mostly because post message was the recommended pattern for I think page document object model to content script communication. I think WebSockets might work. That's why I was interested in WebAssembly as well, seeing if that's something that opened up a channel between the content script and the page document object model. I have not looked as much into it, but it's definitely one possible path to expand the top account approach.
Thank you, Eugene. Any other questions? All right, excellent. Thank you very much.